Alright guys, so today we're going to study how to compute limits analytically. So there's going to be a strategy for this. The first thing you're going to do is you're going to try to evaluate the function. And I'm going to go into details, evaluate. I'm going to go into details as to how to do it in a minute with an example, but that's the general idea. So if you get something of the form 0 over 0, and I have a story for this, you will do this, which means you want to factor. Yes, I know what you're thinking, and I use this all the time in my classes because the reason, the way this happened was when I was a graduate student, I saw that all my classmates were using all these different nice acronyms when they were writing proofs. And I said, oh, I want to do that in class. And I told my students that I wanted to factor, and I wrote that. And they all laughed, and I didn't really know why, because I was new to the US. And then I learned what it meant, and it was terrible. But then I realized that this was a great teaching technique, because you will never forget. If you get 0 over 0, you want to factor, and you will remember it like that. So once you factor or manipulate algebraically, this will stand for that as well, you will cancel the problem. That's what I call it. And once you've done that, you will evaluate again. Now, if it would happen that when you evaluate the first time in your function, you don't get 0 over 0, then you're very likely going to have that the limit will be whatever value you're getting. If you don't get a division by 0 or something that is undefined, then that very likely will be your limit. So let's do a couple examples so we can talk about it. So let me separate this. This is going to be our strategy, and we're going to try to stick to it for the most part. So the first example, this would be if I make a mistake and I give you an exam where it works out to be just evaluating and you just get one step and you're done. That would be great, but very unlikely that that's going to be the case. So let's say limit as x goes to 3, and we get, say, x plus 4 divided by x squared minus 2x plus 2, something like that. And if you look at that, you say, okay, well, my first step is just to evaluate the function. And where am I going to evaluate my function? I'm going to evaluate it at x equals to 3. So that's where I'm going to evaluate my function. So I go ahead and try that. And normally, by the way, we're going to do that on the side. You don't want to write it down there, because you're going to end up getting very likely a division by 0. Not in this case, but very likely you're going to get a division by 0. You don't want to just write that in line as equal to, say 3 divided by 0. That wouldn't be good. That would not be mathematically correct, because you're setting something equal to a quantity that is not defined. You don't want to do that. Nonetheless, in this particular case, we're going to evaluate it here because I know the way I wrote it that it is not going to be, we're not going to have a 0 in the denominator. So x equals 3, 3 plus 4, and then here I'm going to put 3 squared minus 2 times 3 plus 2. Every time I had an x, I plugged in a 3, and then I get something like 7 divided by, here I'm going to have a 9 minus 6, 3 plus 2, 5. Since I just get a number, that's my limit. We're going to take that to be the limit. So that one was kind of a non-example, because sure, you'll have some of those in your homework, but I don't think you're going to get one of those in your exam. So let's do one that you would get in the exam. Example. I was going to write exam. Oh, example. I hadn't noticed ever that. So 2. All right. So example prepares you for the exam. Oh, now I know. All right, so I just learned something. So limit as x goes to, let's go again to 3, and let's do here an x minus 3. Very obvious, I'm putting something that will be 0 there, but that's okay. For the first example, we're good. And let's do something extremely obvious that will be 0 as well when we evaluate at 3. But we want to start to warm up with some easy examples right now. So if I plug it in, and I'm not going to do it here, because, as I told you, I'm going to get a 0 in the denominator, and I don't want to write that as my equal sign. That's kind of like bad manners if you do that. So in this case, I'm going to evaluate at 3, and I'm going to get 3 minus 3. As I said, that's going to be a 0, divided by 3 squared, which is 9, minus 9. So you're going to have 0 over 0. And when you do that, you know that you want to factor. Hope nobody gets offended by that, because I'm saying you want to factor. All right, but what that will allow you to do then, notice, when you factor this denominator, it's a difference of squares. So you're going to have that the factoring will be x minus the square root of 9, which is 3, times x plus the square root of 9, which is 3. So you get that factorization there. And this is the key, that when you're computing the limit, you're seeing where the function is going as x approaches 3, but without ever getting to 3. So if you're never going to be equal to 3, every time you have a number on the numerator that is very, very small, very close to 0, 0.0001 or whatever, you're going to get that same quantity in the denominator, so they will cancel each other. And what that will do is that for every x that is not equal to 3, you actually are getting that the function is going to be equal to 1 over x plus 3. So even though the function does not take any value at x equals to 3, because you get a 0 divided by 0, as you approach 3, you're approaching the value in the y-coordinate to be 1 over 3 plus 3. This first 3 comes from evaluating the function at x equals to 3. And that is going to be 1/6. So the function is approaching the value of 1/6. Does that mean it takes it? No, it does not take that value. So what you would have for this function here is that as you start approaching x equals 1, 2, and 3, 1/6, let's say here, then half, and then divide by 3. So roughly, I'm dividing this into 6. Look at that. So the function is approaching that value of 1/6 here in the y-coordinate, 1/6, but it's not really reaching it. So the function in this case will actually be continuing like so. Not quite, because the asymptote will be at, in this particular case, at -3. So this already, the graph already will be going really, really slow here. So this line would continue here. But nonetheless, my point is that the graph is approaching 1/6 on both sides, even though it's not taking, and this of course doesn't belong there. But it doesn't take the value of 1/6. It just approaches it. So that's what the limit is telling us, that we're approaching 1/6, but we're not quite getting it. And we're just making sense of what the quantity is. So the limit is 1/6. The function does not take the value of 1/6. All right, guys, so here I wrote another example for you guys. So let's go ahead and test this one out. Let's plug 2 for these functions. So we get 2 squared, then minus 4 times 2, and then here I get plus 4. Divided by, I get x squared, so 2 squared, minus 5 times 2, 5x, plus 6. You notice here you get 4 minus 4 times 2. So 4 minus 8 is -4, plus 4 is 0. This one I get 4 minus 10, -6, plus 6 is 0. So I'm getting again something of the form 0 over 0. And that means you want to factor. And so you go ahead and do that. So let's factor here. And this one, our factoring, you notice, is a perfect square. So it's going to be x minus 2 squared divided by, here I have an x minus, which one do I need? I need a 3 and a 2. So x minus 3, x minus 2. Let's see, product is +6, addition is -5. So we're good. So once we factor it like that, we can see that there's a common factor, and the factor is x minus 2, as expected, because this, when you evaluate at 2, that cancels out, or gives you the 0 over 0 rather. So cancel this one out with one of them only. So you have an x plus 2 that cancels one of the x plus 2's in the numerator. And so now, as we said before, the function, whenever x is not equal to 2, you can do this cancellation, and you get that the function is equal to x minus 2 over x minus 3. Now, at x equals to 2, that doesn't happen, but when x is tending to 2, then you do get that the function is tending to, in this case, the function x minus 2 over x minus 3. And this example is really nice, actually. I didn't think about it, but it turned out to be very nice. Because when you plug it in, you get 2 minus 2 divided 2 minus 1, 3, sorry, giving you the answer already. And you get 0 over negative 1. And some people here, because we're doing these divisions of 0 over 0 and all these kinds of things, say, oh, this does not exist. No, you're doing 0 divided by a number that is not equal to 0. This is perfectly fine. This is 0. Now, if you have some number divided by 0, then you have a situation where the limit does not exist. So that, just example 3a, I guess. If you were to do the reciprocal of this function, x goes to 2, and instead of doing the function itself, but the reciprocal, square minus 4x plus 4, then you would get that after you do all the algebra, you end up with the limit, same algebra we did before, you would end up with x minus 3 over x minus 2, and now your 0 would be in the denominator. Well, and at this point you say, well, the limit is not even equal to anything. You simply say the limit does not exist. Because you're going to get negative 1 over 0 when we evaluate for the fourth time, or for the second time in the step 4. So this is going to be that the limit does not exist. So you see the distinction would be, here I have the 0 over a number that is not equal to 0, that is 0. But if you get a number that is not equal to 0 over 0, does not exist. You get 0 over 0, you want to factor. So those are your situations going on there. That's what you need to be mindful of. All right, I'm going to do another example now that is going to involve rational functions, and then I'm going to do one that involves radicals, and that will wrap it up for us today. All right, so let me erase again.